So after we talked about the main control and the shutdown components, it's important here to talk about the last layer of protection, which is the pressure safety valve. Pressure safety valves, or PSVs, are one of the most important components in a process plant. They are considered as the last protection of piping or equipment against overpressure. That's why the sizing, arrangement, and position of a PSV on the P&ID is highly critical and must be carefully carried out. All these depend on the plant arrangement and the expected overpressure scenarios. So, if the safety valve was poorly sized or the overpressure scenario wasn't studied well, we may see an undersized PSV, which means that it shall not accommodate the required flow during the overpressure scenario. So overpressure can still happen in the system, which may cause some failure. Let's get back to the previous example when we had a control valve that reduces the system pressure. So the system upstream, the control valves, has a higher design pressure, and based on that pressure, a higher pipe flange rating, which was 300 pounds, was chosen compared to 150 pounds in the downstream system. Now, if there is something wrong with this loop or the valve fails in the open position, here the downstream system may be subject to overpressure, and that's why we need to protect it. We have already seen that we can use a shutdown system to close the shutdown valve at high pressure. But this is not the only way to protect from overpressure. We can also use a pressure safety valve here. The PSV has a set pressure. If the system reached this pressure, the PSV shall open, allowing the fluid to go to the relief destination, whether it is the flare for gases or a low pressure system for liquids, such as a burning pit, for example, or some vessel that may collect this fluid. So, which method of protection shall we choose? Shall we choose the shutdown system or the PSV or both methods? This mainly depends on studying the system and the overpressure scenario and the reliability of safeguards that we are already having. Here we need to see what is expected to be shown on the P&IDs. So what is the expected information regarding the safety valves that need to be shown on the P&ID? First of all, it's important to show the PSV arrangement. We need to know the number of PSVs. Sometimes one PSV is not enough. In other cases, we may need a spare valve. We may even need more than one valve in operation in addition to the spare PSV, depending on the relief load, the criticality of the PSV, and the operation needs. PSV set pressure is also an important factor, which is the pressure at which the PSV is expected to open. At a lower pressure than the set pressure, the PSV shall not open. Also, the PSV orifice area is expected to be shown on the P&IDs, which represents the size of the PSV and consequently the maximum flow it is expected to pass. If the PSV has a small orifice area and it couldn't handle a relief load at an expected scenario, then overpressure is still expected to occur, and the PSV will not be adequate in this case to protect the equipment. The PSV designation for P6 here represents 4, which is the inlet PSV nozzle, P, which represents the valve orifice area, and 6, which is the size of the PSV outlet nozzle. We can also add PSV sizing case, which represents the overpressure scenario. This can be fire, blockage, thermal expansion, etc. The overpressure scenario is important to be taken into consideration because it has a direct effect on the size of the PSV. So, if the PSV is sized based on thermal expansion scenario, for example, and we are currently studying an overpressure due to blockage, then in this case, PSV would not be considered as a safeguard, because most probably it shall not be adequate to handle blockage scenario, since thermal expansion is not sized based on high relief load. Its relief load is too low. So in this case, we may need to add another safety valve or replace this valve with another one, which has larger orifice area that is suitable to handle the relief load for blockage case. Showing this data on a PNID is highly important, as this may affect the decision whether there is enough protection for the system or not. If the data wasn't accurate, this may lead to an unprotected system which is vulnerable to overpressure, and this may cause a severe issue in the plant.